Hello and welcome to another lecture on generating functionality by Herbert Wilf. My name is Hunter Ream and I will be talking to you about section 1.6 called another two-variable case. In this section we plan to come up with the closed form for the Stirling numbers and the Bell numbers. Let's talk about the Stirling numbers first. So as a definition, for a positive integer n, define square bracket n to be all of the integers, positive integers, up to n. Then the Stirling number, so the nk Stirling number, denoted by curly bracket nk, is the number of partitions of n, square bracket n, into k sets. So we're defining the nk Stirling number here. And as you can see, this will create a this will create a sequence. So either we could range over n or we could range over k, and so there's a couple different generating functions you can come up with, but the one that we're going to be defining today, another definition, define bk of x to be equal to the sum over n of curly bracket nk x to the n. And this is a generating function. So this is going to be our generating function for the Stirling numbers. And notice we're ranging over n. Sometimes it might feel more natural to range over k in this case, but let's just start by fixing a k and ranging over n. So we want to find, first thing that we want to do is we want to find a recurrence relation. And the reason we want to do this is because this is how we're going to be able to use the generating function to find a closed form for the Stirling numbers. So let's find a recurrence relation. How we're going to do this is we're going to think about all of the partitions sitting in front of us. And we're going to try to come up with two different completely disjoint sets. And these will be very naturally disjoint. On the left-hand side, let's consider all the partitions with n in its own set. And by this I mean, I should say, instead of its own set, let's say its own class, where partitions consist of k different classes. So here, since all the partitions are sitting in front of us, and we're just choosing the partitions that have n in its own class, then really there's only k minus 1 more classes to be choosing, right? So the number of elements, the number of partitions in this set over here is going to be, well, I'm only choosing k minus 1 different classes, but I'm also only choosing it from n minus 1 different elements. So we're going to have n minus 1, k minus 1 different elements over there. And so, and then on the right-hand side, here are the rest of the sets, or the rest of the partitions. And now we need to think about, well, how many different partitions are left? And it's helpful to think of it as, well, the one on the left had n in its own class. So certainly on the right, that is never the case. It's never the case where n is in its own class. That means that n is in one of the k classes, always. And so if we just said, okay, let's take all of the partitions where n is in the first class, well, then we're still choosing k partitions. That's still the case that we're choosing k different partitions, n is just in one of them. And it's possible that other elements land in that first partition. But we're only going to be choosing it from n minus 1 different elements. But notice that I only said that n was in the first class of a partition here. So it's possible that it's also in the second, or the third, or any of the k different classes in each of the partitions, which means that, sure, what I have written down in the circle on the right, that's how many there are if I fixed the class that n was in, but there's k different possibilities there. So that means there's k times n minus 1k different partitions there. So this leads us to a nice recurrence relation. So here, I'll go to the next page, and, oops. So the next page, so we'll do, let's say, so we have the relation of, well, nk is going to be equal to n minus 1 k minus 1 plus the other set, k times n minus 1 k and curly bracket. And now we're just going to do what we always do with generating functions. We're going to multiply by x to the n, and we're going to sum over all n. So we're going to do this on both sides of the equality. So multiply by x to the n, sum over all n. Let's do that, and we'll split it up by linearity immediately. Get our x to the n, okay, and we're summing over, and I should make this equal, k, n minus 1k, x to the n. And so why we would do this, well, on the left-hand side, that is identically bk of x. And on the right-hand side, we need to do a little bit of algebra to make it look like some bk, maybe bk minus 1 of x. So the first term, that is this term right here, what we're going to do is I notice that normally the n that is inside of my Stirling number and the n, which is the exponent on the x, they normally match. At least I want them to. And right now, they don't match. We have an n minus 1 and an x to the n. So to make them match, we're going to have to pull out an x. So if I pulled out an x, factored one out, then this would look identically like b k minus 1 of x. And our last term, well, this looks pretty close as well. And again, it's the only thing that is missing is the fact that we need to let that n minus 1 and n match. So again, I'm going to pull out an x, but this time we have our k there, so it's slightly different. and it will be b, this time, k of x. And I'll point something out that down here we have a k minus 1. And the reason we had a k minus 1 is because of this. Well, here we have a k, and I'm not just arbitrarily assigning a subscript to this. This k matches this k here. Just like this k matched this k here. Alright, well, this is helpful because I think we can now come up with a recurrence relation for bk now. So we had a recurrence relation for our Stirling numbers. Now we even have a recurrence relation for our bk's, because if we take this equation and solve for bk, I'm not going to work out the algebra, but we get x over 1 minus kx times bk minus 1 of x, which is a recursive formula. So, by induction, or however you choose to think about this, we would end up getting that bk is equal to x to the k all over 1 minus x, 1 minus 2x, dot dot dot, all the way up to 1 minus kx. And you can imagine that starting, if this isn't super clear to you right off the bat, you can start putting in some elements for k here and see that really this is exactly the formula that's going to be generated. Oh, I should really say of x. Well, this is nice. It's a closed form for our generating function, but this isn't really what's helpful, because what we want is we want to be able to use the generating function to somehow equate coefficients of certain power series. But this is hard to form a power series out of. Although, one of the techniques that we learned in calculus would be partial fraction decomposition. And we can do that in general here. So we're going to use partial fraction decomposition. Let's say partial fraction decomp. And, well, let's not worry about the x to the k in the numerator. Let's just focus on splitting up the denominator. We'll write this out. And we want to be able to write it as a sum. We'll say over j with some coefficient in the numerator, let's call it alpha j, over 1 minus jx. So I'm really just taking each of these pieces here, which is this one, this one, this one, and I'm splitting them up as a sum. Just like we would do with partial fraction decomposition. And how we would solve for these alpha j's is we're going to multiply both sides by 1 minus rx, and let x be equal to 1 over r. So the purpose of this, we're going to clear the denominator on the left-hand side of the term 1 minus rx, and then we're going to input 1 over r for x. And since we cleared the denominator, we don't have to worry about dividing by 0. It'll also clear all of the terms that we don't want. And if you work it out, not much to work out here. I'm really simply just plugging in 1 over r. We get 1 minus 1 over r. It's supposed to be an r. Minus, or sorry. So this is just going to be multiplied by 1 minus 2 over r. So on. But this gets a little long to write out because we want to denote that we're going to be actually skipping the rth component down here, right? So we had we have r minus 1 over r, and then we skip r over r, and we just go to r plus 1 over r. Okay, we can continue. 1 minus, and we go up to k over r. And we'll make this a little longer. Okay. So we're going to use this because we're going to be using this side over here to be the generating function. It's a more useful version of it. So some things to note. Some things to note is this. So we have, we'll go to a new page here. So the Stirling number, let's just kind of recap what's happening, is going to be equal to the coefficient on x to the n of our generating function. And this piece is by definition. Or at least by definition of the generating function, because that is exactly how we define the generating function. Now, what's nice is we know what that generating function looks like. There's a couple ways to write it. Let's start by writing it like this. We have an x to the k all over 1 minus x dot 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 1 minus kx. But instead of taking the nth coefficient, the coefficient on x to the n of this function, we'll take the coefficient on x to the n minus k of just 1 over 1 minus x, 1 minus kx, which will give us the exact same coefficient, but it's just viewing it from a different light. And the reason we would want to do this is because we actually know what this looks like. We know that this is going to be the coefficient on the n minus k term of our sum. Which is alpha j all over 1 minus jx. Oops. Well, and we know what this looks like explicitly, right? Because, well, instead of having this coefficient on the outside, it's not necessary. We can kind of combine like terms at the end and put this in. So let's go over r. Let's go over r. We'll be switching the index. It's not going to change the expression at all, but I'm going to move this inside and we're going to go over r. Alpha r, coefficient on n minus k of, well, 1 over 1 minus rx. And I'll put parentheses around this for emphasis. But we know what this looks like. This is exactly the formula we use for geometric series. So I'm just going to copy this down. The sum from alpha r, but the n minus kth coefficient, the coefficient on x to the n minus k of this geometric series is going to be identically r to the n minus k. So if you don't see that immediately, expand this out as a power series instead of looking at it in this closed form, and then just take the n minus kth coefficient. So the only thing that's not as well defined in the formula we have at the moment is alpha sub r. I mean, we actually know what alpha sub r is, so let's write that out because that'll be helpful. So let's rewrite the sum. And so what is alpha sub r? What I'm going to write is a version of alpha sub r. I'll describe what I'm going to be doing in a second here, but the denominator is going to look slightly different. I'm writing r minus 1, r minus 2, dot dot dot, r minus 1, r minus r plus 1, skipping over that rth term again, and last term r minus k. And how I got to this from alpha sub r was I multiplied by r to the k minus 1 over r to the k minus 1. And that's just cleverly multiplying by 1, but it clears the fractions inside of the fractions, which can be a pain. And then we get this formula, which is a lot nicer in my opinion. On the outside here, we have an r n to the k. And so let's see what happens here. Well, if we combine the terms that we see, the r's at the very least, we can at least rewrite the numerator as r to the n minus 1. And I'll just draw a line for now. And I want to point out that these first couple terms here, well, I don't know how many there are exactly, but, well, sure we do. We start with r minus 1, then we subtract 1, we multiply by r minus 2, and so on. We go all the way down until we do r minus 1. So this term, r minus 1, you can figure out that that's just 1. So if we multiply r minus 1 and we just keep going down all the way until we get to 1, that's just taking the factorial of r minus 1. Now over here, just past that, it appears like we're getting negative, right? We're getting negative terms because it's possible that k is actually bigger than r. So what could be happening here is that this term could be negative, this term could be negative, and so on. But if we look at it going backwards, we're taking r minus k, and then we come back, and we're now subtracting numbers from r minus k going this way. So really we have, I'm going to switch them to be positive so that instead of these numbers on the right hand side being negative, well, I'm going to switch them to make them positive, take the factorial, and to account for that, I'm going to make sure that each time I'm multiplying by the appropriate negative 1 value. And that just preserves the polarity of it. And now this formula is starting to look pretty nice. And what I'll actually do, just to make it look even nicer, is I'm going to multiply by r over r to make this simply r to the n negative 1 raised to the k minus r all over. Now, since I multiply by r over r, we get an r factorial. And still our k minus r factorial. And this is going to be our formula, actually, for when n and k are greater than 0. Notice here that there's actually no criterion for k being bigger than n, even though the way we defined these numbers, that's the only way it would really make sense. We're going to use that, and this is actually going to come out of this formula explicitly, that when k is larger than n, well, that number is just going to be 0. So our conclusion, we can conclude by our string of equalities above, and I'll just kind of rewrite it, is that the Stirling number, the kth Stirling number, is going to be identically equal to the sum from r equals 1 to k of negative 1 k minus r to the k minus r times r to the n all over r factorial k minus r factorial. And so a good way to remember this, we use this notation. It looks very similar to the choose function, and even the formula that we have written here, it somewhat looks like what the choose function looks like when we define it. And why do I say that? Well, with the choose function, we normally have this something factorial times something minus something factorial, right? That's a thing. We don't really have this extra decoration up here, but we kind of do. So we're just summing over things that look like the choose function. And we're going to be seeing this, so we want to be able to remember what this looks like. So that pretty much concludes the Stirling numbers. And in the beginning of this, I said that we were also going to be defining the Bell numbers, so that's actually what we're going to move on to now. So we're on a new page, so let's go ahead and define the Bell numbers. So the Bell numbers let's actually say the nth Bell number denoted little b of n is the number of partitions of square bracket n. It seems very similar to the Stirling number, except for here we're not fixing any number of classes. We let that range entirely over. we let k range entirely. In fact, it is true that b of n is identically equal to, and you can think about this, the Stirling numbers and k as we range over k. But we just said that it doesn't matter if k is larger than n. That will just evaluate to 0. So we can do that actually. We can still range over k, but as long as, so what I'm writing is we can sum from k up to any m as well, as long as m is, looks like a subset, but I mean see, is greater than, n. Greater than or equal to n. This will be true. And we're going to use this because, in particular, let's say, okay, so b of n, I'll rewrite this, but this will be very useful. Capital M of nk, and now I'll start a string of equalities here. So I know what nk is, the Stirling number. We just came up with the closed form, so let's write down that closed form. Unfortunately, that closed form involves a sum, but that's alright. We're not afraid of double sums. So we'll go ahead and write it out. -1 to the k minus r times the quantity r to the n all over r factorial k minus r factorial. So now what we're going to do is we're going to aim to shuffle around these elements. And in particular, what we're going to do is in the inside here, there are going to be certain values of r. And yeah, I mean, r ranges from 1 to k, but k also ranges from 1 to m. So there's going to be seemingly a lot. If I were to write this sum out entirely for some fixed m and for some fixed m, then sure, this r, there'd be a lot of different r's in there. What we're going to do is we're going to group all of those r's together. So if we fix some r, then we're going to be able to, so how I'm going to denote that is, let's consider all of the values of r. Well, since r ranges from 1 to k, but k ranges from 1 to m, well, it's definitely possible, and it's going to happen, that there'll be different values of r ranging from 1 to m. So let's group those together. If we start at 1, well, what we're going to do, we'll notice that if the only things that don't also depend on k are the values r to the n and r factorial. So that is this piece right here and this piece are the only two that don't depend on k. This one depends on k and this one depends on k. So if I were to group all of the elements r together and factor them out, well, they would be constant in this sum here. So I can actually factor that out. And what would be left would be the values from k equals r up to m. And the reason we started at k equals r is because this, if we fix some element r, this is going to be the only thing that's left. This is only going to show up when k is in particular bigger than or equal to r. And so what's going to be left is, well, the rest of it. Negative 1 to the k minus r. That's supposed to be an r. All over k minus r factorial. And so if that's not clear, I suggest you work out an example. You know, let m equal 4 and n equal 3, and you'll see that all you need to do is group all of the r, the ones, if you fix some element r and group them all together, you'll be able to factor this term out, and you'll see what's left. And this is exactly what's going to happen. So we get this nice equality here. And the reason this is nice is because I can rewrite that last sum, the sum that's on the inside, as, well, instead of going from k equals r up to m, I mean, we see on the inside that there's a k minus r here, there's a k minus r here. Let's start at some value s equals 0, because that's definitely going to be the case down here and right here, that, well, when r is equal to k, this will be 0, and so will this. So it starts at 0, and it'll go up to m minus r of the same sum, same thing, but instead of writing k minus r, we're just going to write s and s factorial. Now, why, and I said you'll see this in a second, I mean, I guess it's been longer than that, but coming back up here, I really insisted on making this m be larger than n. And why did I do that? Well, the reason I did that is because it doesn't matter how large m is. Since it doesn't matter how large m is, then we can actually take m as a limit to go to infinity. It doesn't matter. I mean, that sum will be the same, because if we go back up to the top, well, if k is larger than n, it's just going to evaluate to 0 anyways. It doesn't matter if we take m to infinity, this will still be the exact same sum. So doing that, this piece right here, taking m to infinity, will just evaluate to 1 over e. So I'm going to rewrite b of n, and I can factor that out, and what would be left is the value when r is greater than or equal to 0 of r to the n all over r factorial. Which is kind of cute. I mean, honestly, it's like, it's a sequence, or it's a series that we've maybe seen before. It looks really, really nice, but it's also not really practical. Like, we can't do that much with this, and because we would have to actually evaluate an infinite series in order to generate these numbers, and that's not that useful. So yeah, sure, this is a closed form, but we want to come up with a recursive formula for this, for these Bell numbers, that is more practical, something that we can actually work with and compute. So what we have to introduce here in order to do this is we have to define, well, the thing that we've been using is if a sub n So let a sub n be a sequence. This is really, we've been using it, but the ordinary, we'll call this the ordinary generating function, for this sequence a sub n is the sum when n is bigger than or equal to 0 of a sub n x to the n. The exponential generating function, on the other hand, for the same sequence for a sub n is, well, it looks very similar. We're still going to range from n equals 0 onto infinity, but the terms, we're actually going to just put this n factorial in the denominator, so a sub n over n factorial of x to the n. We'll go to a new page. So why would we do this? Well, there's an actual reason that we're going to do this, so let's go ahead and define b sub b of x, capital B this time, n equals 0. We're defining it to be what we know the Bell numbers are over n factorial x to the n. So we're going to try to come up with a formula for little b of n now. And so we're going to do what we normally do, and this is an exponential generating function now. So instead of just multiplying by x to the n with some formula, well, we have this formula, right? So I guess this is what I'm trying to say, is we have b of n, and in particular b of n is equal to 1 over e, the sum from r equals 0 on to infinity of r to the n over r factorial. So I'm going to take this and multiply by x to the n over n factorial. And I'm going to sum over all n greater than or equal to 0. Let's actually, instead of doing that, let's sum from n greater than or equal to 1. This will work out better. And we're going to do the same on the right-hand side. So I'm just going to pull out this 1 over e factor as just a constant, so it's not going to make a difference where it is. But if I range from n equals 1 on up, and r equals greater than or equal to 1, greater than or equal to 0 actually. We have, well, yeah, we should really write it like this. We have our x to the n factorial here, and then we have our sum. So we multiply by x to the n over n factorial, multiply our sum by that, and we get this. Well, we can combine some like terms here, at least put the sums together, and then combine the terms, so we get an xr to the n all over n factorial r factorial. And now I'll pull out that r factorial. Now we can actually switch the sum, because some of you might question me a little bit here, but what we're doing is we're just kind of pushing around symbols. So you might be worried about convergence here, but I challenge you just not to be at the moment worried about the convergence of them, and let's just push the symbols around. We're dealing with this formally, so we can just switch the sums if we want. and pull out a 1 over r factorial. And on the inside, we're still left with our x r to the n all over just an n factorial this time. But the reason we want to write it like this is because this looks exactly like the power series for e to the x, or at least e to the rx. So I still have this sum, but this piece, and I'll try to circle it with my little highlighter here, but is that this piece is going to be just over 1 over r factorial, but this is going to be e to the rx. But notice normally when we're defining the power series, we start at 0, and this one starts at 1. So we have to add and subtract 1, so in order to do that, we're just going to subtract 1 from this. But we want to be able to write it like this. I mean, it's way better to write it as e to the rx minus 1, as opposed to this infinite series. And so just distribute. We get, I'm going to leave my 1 over e on the outside here, but on the inside we have the sum from r bigger than or equal to 0 of, well, let's distribute this in. We get e to the x, and we'll rewrite it a little bit. Nothing drastic. As e to the x to the r, instead of just e to the rx, all over r factorial. This is just a sum, so let's go ahead and distribute. We have a 1 over r factorial. And you can think of this as 1 to the r. I mean, that doesn't harm anything. I like to think of it that way because this then looks like, well, e to the x, if you just expand this piece out to be the power series of e to the u, or e to the blank. And over on the right hand side, we just have e. And then if we just distribute our 1 over e, we get e to the x minus 1, in the exponent that is, minus 1, and that's in the base. But notice what I've been doing. I mean, I just been simplifying the right-hand side of the original equation that I wrote. On the left-hand side, I haven't been writing anything. And really, I've just been saying this thing is equal to this, and so on, aligning my equalities. But that left-hand side, it looks a heck of a lot like our original generating function, but it's just off by a term because we started at 1. So what I'm going to do is I'm going to, write b of x, but we had to add and subtract a 1, so I'll just write minus 1, and that is identically equal to this last piece here. e to the x minus 1 minus 1. Oh, well, since there's a minus 1 on both sides, we just get then, so thus, b of x is equal to e to the x minus 1, which is a really nice closed form for the generating function. I mean, that's satisfying in itself, but I mean, why is that useful? There's got to be a reason why this is useful, and the purpose of it is to be able to do what we did before, which is somehow write this as a power series and equate the coefficients. So the thing that we're going to be outlining here is called the ExDX Log operation. We'll underline that because it's important, and it's just the motivation behind it is really just that we want to be able to equate some coefficients, and this is going to be a really nice general way to do that. So first we'll take the logarithm of both sides. Second thing, we're going to differentiate both sides. and multiply by x. So they multiply through by x. We'll clear denominators, clear the equation of denominators. And lastly, we'll just equate the coefficients. So let's draw a line here, and let's do these steps for our specific example. I said that we wanted to take the log of both sides. So if we take the log of the left-hand side, I mean, nothing changes at the moment. We'll just rewrite it. But the right-hand side, that's nice. I mean, it just, if we take the natural log in particular, then we just get the exponent. Now what do we want to do? I mean, the second step says differentiate both sides. If we differentiate the natural log, in the denominator we get exactly what's on the inside. You know, we're using chain rule here to actually differentiate this. Nice algebra, or nice calculus exercise. And by the chain rule, we're going to have to multiply by the derivative of the inside function here, which is just going to be, we can multiply this term by term. So we're going to write our coefficients, which are b of n factorial. Then we're just going to differentiate x to the n, which is just going to be a n times x to the n minus 1. And this will be equal to, well, e to the x. Because notice I didn't write the negative 1 because I differentiated it. So I differentiated e to the x minus 1 to get e to the x. Just so we have an x to the n in the numerator on the left-hand side, I'm just going to multiply both sides by x, which is what this says to do, is multiply through by x. So I'm just going to erase that minus 1 because I'm multiplying through by x, and I will also write an x here because, well, we want to make sure they're equal. Step 3, clear the denominators, right? So I'm just going to write the left-hand side, the numerator of the left-hand side, and that'll be equal to x e to the x, sum n greater than or equal to 0 of, well, I'm just rewriting the denominator now, which was on the left-hand side before, now is on the right. And it's hard to see this in the moment, and for now, we're just going to have to trust the process and understand that multiplying this x e to the x, well, we can expand this out as a power series, and then we can multiply it by this power series, and there's a general formula for that. And I'm not going to walk through that at the moment. We'll talk about that at some point in a different video. But if we multiply this power series, the power series of this times this power series, we'll get different coefficients. And we're just going to equate the definitions that we get, equate the coefficients that we get, and solve for b of n. And what we end up getting, and this maybe will be slightly unsatisfying at the moment, but if you know how to multiply power series, you should work it out and just solve for b of n, and you'll end up seeing that we get the sum over k of n minus 1 choose k of b of k. So that's a nice recursive formula for the Bell numbers, and that is actually, in practice, more useful than trying to evaluate some infinite series like we had before. I think this is a little bit better, a little bit more useful. And that concludes section 1.6.